Hey, hello everyone. So today we are going to start with memory management. But before that, I want to address that it has been a long time since I streamed last. It's partly due to like it's the marriage season, and I've been enjoying myself a lot actually. Let's frame it in that way. And secondly, I recently got a scholarship for this course by Arden Labs, and it's actually a very good course, and its original price is $1,200, which I'm getting for free. So, uh, I, like anytime you get something new, you are excited to learn. So I was learning Lang there. I completed the first section there, and it's actually I'm quite impressed. Not only because I'm getting it for free, but I'm genuinely very impressed. As that like it's not a sponsor or anything. So I'm genuinely very impressed the way they teach, and I've heard the second like the courses like there are total of 10 courses, and um two like trainers teach us. So I've heard that the second course is taught by the second teacher, and he is actually the founder of Arden Labs, one of the co owners. So I have heard that he's actually like much like he's also like this itself, like the first section was itself uh, like a lot very good, and then he's actually much better. So uh I'm excited. So it has been a mix of both, where I was excited to learn that, and I didn't feel like doing JavaScript at that time, and also I've been in like a lot of I've been enjoying myself a lot, and going to do like matches and all that. So let's start with memory management. And what do we say about memory management? Because mostly JavaScript has a garbage collector, which does most of the jobs. But I guess they'll talk about that. Yeah, they have garbage collection here, and but it's important to understand that how it does that, because a lot of language don't have a garbage collector. Plus, um computer science concepts probably, and mm, making like JavaScript is also a very memory leaky language, where you can have a lot of memory leaks. So we need to prevent that. So that's also important. Um, C has malloc and free, and in contrast, JavaScript automatically allocates memory when an object is created and frees it when they are not used anymore. Garbage collection. This automatically is potential source of confusion. It can give developers the false impression that they don't need to worry about memory management. Yep. Regardless of programming language, the memory life cycle is pretty much always the same. Okay. So mostly all languages have same memory. Allocate memory, use allocated memory, release allocated memory when it's not needed. The second part is explicit in all languages. The first and last part are explicit in low-level languages. But mostly implicit in high-level languages like JavaScript. So what a lot of people nowadays do to manage like memory management, they use serverless functions, where like what serverless does is that let's say what happens no in normally in your case you create a server which is always active, and whenever there is a like and you fire REST APIs, and the server responds. But what serverless does is that whenever you call up the REST API, it creates a new process, and then it terminates like as soon as the job is done. So each like for every request a new process is created, and that's terminated. So that manages garbage collection very well, because uh, everything is contained in that process. Allocation of JavaScript. Value initialization. In order Do not bother programmer with allocation. JavaScript will allocate memory when value is initially declared. Allocates memory, allocates memory, allocates memory. Uh, this also allocates memory. Takes a allocates a function which is a callable object. Okay, expression also allocates an object. Yeah. Allocation via function calls some new date allocates memory. Basically different types of memory, but some methods allocate new values or object and new string. Strings are immutable values. JavaScript may decide to allocate a memory, but just store the range. Okay, cool. Okay, so like I think JavaScript sometimes optimizes, uh, like sometimes it will store the whole string, or and sometimes it might store only the range. So that's like something very internal to JavaScript. Uh, I don't think that will cause any problem you to conquer. Yep, using values. Using value basically means reading and writing. This can be done, yeah, we know. Release when memory is not needed anymore. The majority memory manager issues occur at this phase. Most difficult aspect of stage is determining when the allocated memory is no longer needed. Exactly. Because if you do that too early and then we need that memory, then that's a problem. Low-level language require the developer to manually determine at which point in the program the allocated memory is no longer needed and to release it. So in C we have the free method. In C++ we have delete. So that's how there we manage memory. But still, a lot of times that there like a lot of developers forget to delete or free, so that creates a lot of problem. I like this in Golang a lot, because I'm learning Golang right now, where uh, everything like if you have to free up memory, you have to just like you have to, like it's not a compulsion, but you can also forget there also. But normally you defer and declare that the free up of memory there, and then like just at the next statement. So whenever you have to free up memory, then you can remember that. So it's a nice like way. um, there. Like Golang has its own benefits, so also has its own demerits, also in my opinion. But yeah, that thing I liked a lot, where like you take up memory and you defer like you open a file and you defer the in the next statement itself you defer the close of the file. So that's more rememberable, and it's like I think most developers will remember to do that. Some high-level language, such as JavaScript, utilize a form of automatic memory management known as garbage collection. The purpose of garbage collector is to monitor memory allocation and determine when the block of allocated memory is no longer needed and reclaim it. This automatic process is an approximation, since the general problem of determining whether or not a specific piece of memory is still needed is undecidable. Okay. As stated above, general problem of automatically finding whether some memory is needed or is undecidable. As a consequence, garbage collector implement a restriction of solution to a general problem. This section will explain the concepts that are necessary for understanding the main garbage collection algorithm and their respective limitations. Okay. I don't understand why it's undecidable, because, in my opinion, like, uh, if the function closes where it the variable is declared, it should not be needed. Let's see if this is something that uh, is the case, because let's say I write I open a file in the main function. So at the end of the main function, it should be closed automatically, or like that memory space should be freed up. So that's how I think it should work. But I do understand that sometimes, like, you want to do that earlier, so that could be a problem. Like, you want you are not using the file, like, let's say after you call up, like, open the file, you call up a function using that file, and then you do, or like, write 10 million lines and you don't use the file. So at that point, you uh, like you don't need that file at that point. So I guess that would be a problem. But yeah, at the end of the main, or at the end of the function where the variable is declared, like, the memory is taken, I don't think at that point, like, there should be a confusion. But yeah, I do get some confusion, but not a lot. Yeah, but yeah, my like, at the end of the function, it might not be that efficient as we want. So that's also a problem. The main concept of garbage collection algorithms rely on the concept of references. Within the context of memory management, any object is set to reference other object if the former has access to latter, either implicitly or explicitly. For instance, a JavaScript object has reference to its product implicit reference, and to its property values explicit reference. In context, the notion of an object, I'm sorry, is extended to something broader than regular JavaScript object, and also contains functional scope or global lexical scope. Reference counting garbage collection. This is the most naive garbage collection algorithm. This algorithm reduces the problem of determining whether or not an object is still needed to determining if the object still has any other object referencing it. Any An object is said to be garbage or collectible if there is zero reference pointing to it. For example, let x is equals to a, and a is an object. Two objects are created. Y is equals to x is equals to 1, z is equals to y dot a, y is equals to Mozilla. Okay, so let's read the comment. Two objects are created, one referenced by other, one of its property, other is by virtue of, obviously. No garbage collection. Y. Y is X. Okay. But hmm. Reference to a property or object. This object now has two references. One as a property and other as Z variable. Yeah. Y is equals to Mozilla. So now nothing references this object, this whole object. Reference to it. It can be garbage collector. However, its property is still referenced by a Z variable, so it cannot be free. That is question none. The A property of object is originally in X, has zero reference to it. It can be garbage collected. Yeah, so what's the problem? Like this, I think this is a good implementation. Let's see what are the limitations. There is a limitation when it comes to circular references. In following example, two objects are created when properties are referenced one another, thus creating a cycle. When we go out of the scope of the function call has completed, at that point they become unneeded and their allocated memory should be reclaimed. However, referencing counting algorithm will not consider them reclaimable since each of two objects has at least one reference pointer to them, resulting in neither of them being marked garbage collection. Circular references are common cause of memory leaks. Okay, I okay. Don't do circular references, and mm, I guess this problem would have been solved till now. But I do get okay. Reference counting garbage collector, which have caused memory leaks and circular references. No modern engines use reference. Okay, cool. Mark and sweep algorithm. This algorithm reduces the definition of object is no longer needed to an object is unreachable. This algorithm assumes a offset of object called roots in JavaScript. Uh, the root is a global object. Periodically, garbage collector will start from these roots, find all objects that are referenced from these roots and all object reference from these, etc. Starting from the root. The garbage collector will thus find all reachable objects and collect non-reachable objects. This algorithm is an implement improvement over previous ones since an object having zero references is effectively unreachable. The opposite does not hold true as we have seen with circular references. Yep. Currently, all modern engines ship a mark and sweep garbage collector or improvements made in this field of JavaScript garbage collection generally. eh, Over the last few years are implementation improvements of this algorithm, but not improvement over the garbage collection algorithm itself, nor its reduction of definition of when an object is no longer needed. The immediate benefit of this approach is that that cycle is no longer a problem. In the first example above, after the function call returns, the two objects are no longer referenced by any resource that is reachable from global object. Consequent, two objects, uh, the two objects are no longer referenced by any resources that are reachable from global object. Cool. Consequently, when they will be found unreachable by garbage collector and have their allocate memory reclaimed. However, the inability to manually control garbage collection remains. There are times when it would be convenient to manually decide when and what memory is released. In order to release memory of an object, it needs to be explicitly unreachable. It is also not possible to programmatically trigger garbage collection in JavaScript and will likely never be within the core language, though engines may expose APIs behind the opt-in flags. Yeah, why couldn't we just do it ourselves? Like I do understand, like sometimes giving like power additional powers to the voice developers cause problem, but uh, like this could be a good thing actually. Like probably something else. JavaScript engine typically offers flags that expose the memory model. For example, Node.js offers additional options and tools that expose the underlying V8 mechanism for configuring and debugging memory issues. This configuration may not be available in browser. Yep. The even less so for web pages via HTTP headers, etc. The max amount of available heap memory can be increased with a flag. Okay, this is how we increase the max amount of heap memory. We can also expose the garbage collector for debugging memory issues while using. Okay, how do we do it in the Chrome developer? Let's see. Although JavaScript does not directly expose the garbage collector API, the language offers several data structures that indirectly observe garbage collection and can be used for memory usage. Yeah, weak maps and weak sets. We did this. Weak map and weak sets are data structures whose API closely mirror the non-weak countable map and set. Weak maps allow you to maintain the collection of key value pairs, while weak sets allow you to maintain the collection of unique values, both with performant addition, deletion, and querying. Weak map and weak sets got name of from the concept of weakly held values. If X is weakly held by Y, it means that although you can access value of X via Y, the mark and sweep algorithm won't consider X as reachable if nothing else strongly holds to it. Most data structures, sorry, except the ones discussed here, strongly hold to object paths in so that you can retrieve them from any time. The key of weak map and weak set can be garbage collection. For weak map objects, the value would be eligible for garbage collection as well. Okay. As long as nothing else in the program is referencing the key. This is ensured by two characteristics. Weak maps and weak sets can only store objects. This is because only objects are garbage collector. Primitive values can never be found. Uh, Forged, this is one is equals to one, but yeah, making them stay as in the collection forever. Weak map and weak sets are not iterable. They prevent us using yeah to observe the liveliness of object or get hold of arbitrary key which should otherwise be eligible for garbage collection. In typical explanation of weak map and weak set, such as one above, it often implied that key is garbage collected first, freeing the value for garbage collection as well. However, consider the case of value referencing key. Key is an object. Okay. Now key cannot be garbage collected because the value holds the reference to the key and the value is strongly held in the map. If key is sorted stored as an actual reference, it would create a cyclic reference and make both keys and values ineligible for garbage collection, even when nothing else references key. Because if key is garbage collector, it means that some particular instant value dot key would point to existent address, which is not legal. To fix uh, the entries of weak map and weak set aren't actually references but M F F F ephemerons. Okay, what are ephemerons? Bruh, she used to help to make finalization more useful and people define the most. Ephemerons are similar to weak pairs but are objects in ephemerons key field may be classed as almost collectible even if the it is reachable from ephemeron value field. Okay. An enhancement to mark and fill sweep mechanism. Barrows, okay. Basically, in like simpler terms, ephemerons make this possible to be garbage collected. Basically, like if this is the case, it will be garbage collected. This is not a perfect, not one minute. Let me take a call. Okay, class week, my week ma'am. Marker is equals to symbol, my week ma'am. Get is a key returns key this dot marker. Set key value has delete. Okay. As you can see, my week map never actually holds a collection of keys. Hmm. It simply adds metadata to each of. Okay. Object being passed in. The object is then garbage collected table via mark and sweep. Therefore, it's not possible to iterate over the keys in weak map. Nor clear the weak map, as that also relies on the knowledge of entire key collection. Weak grips and finalization registry. Weak reps and finalization registry offer that introspection into garbage collection mechanism machinery. Avoid using them wherever possible because the runtime semantics are almost completely unguaranteed. Yep. Uh, okay, this is small. All because whenever I find this like avoid using them. It's mostly non-usable. Like the thing that's like we never use. So, but obviously knowing it also helps. All variables with an object as values are references to an object. However, such references are strong. Their existence would prevent the garbage collector from making the object as eligible for collection. A weak ref is a weak reference to an object that allows the object to be garbage collected while still retaining the ability to read the object contained during lifespan. Wow. Okay, cool. One use case of weakref is cache system, which maps string URL to large objects. Okay, we cannot use weak maps for this purpose because weak map objects have their key weakly held, but not their values. If you access a key, you would have always deterministic get of the value, since having access to key means it's still alive. Here we are okay with to get undefined for a key if the corresponding value is no longer alive, since we can recompute it, but we don't want unreachable objects to stay in the cache. Okay. In this case, we can use a normal map, but with each value being weakly ref to object instead of actual object value. New map return is in key. If cache has key, is done cache.get dot the ref value await getter key cache dot set. Okay. Finalization registry provides an even stronger mechanism to observe garbage collection. It allows you to register objects and be notified when they are garbage collected. For example, for cache system exemplified above, even when the blobs themselves are free for collection, the weak ref objects that hold them are not, and over time, the map may accumulate a lot of useless entries. Using final registry allows someone to perform cleanup in this case. Okay, map from string URL. Every time after the value is garbage collected, the callbacks are called with the key in the cache, allowing us to remove the cache entry. Registry is a final key if cache not been. Ref cache dot delete key. Okay, so every time um this is the ref the we've deleted. Due to performance and security concern, there is no guarantee of when the callback will be called or if it will be called at all. This should not be used for cleanup and non-critical cleanup. There are other ways ways to more domestically resource manage such as try finally, which will always execute the finally block. Yeah, so normally what you do is like if you want to open a file, let's say, so you add the try catch block and you add the finally block at the end, and there you close the file. So that's actually much simpler and less, like I guess they are also recommending that. For more information on API of Weakref and finalization registry, see the reference. I guess that's it. It's been a long time, so like I was having some problems with like reading it for the song. But yeah, we are done here. Last topic that's left uh, is a fairly like small topic, the event loop, but it's heavy, very important. It's actually one of the most important topics, and we'll do this, and that will complete our course. I have had two requests for the TypeScript, and one request for React and one for Node. So let's see what we might take next. I have a Telegram channel now, so you can go on there and write in your suggestions. And let's see. Bye bye.